All right, 4.6 is on confidence intervals. What we're going to work on today is how do you calculate a confidence interval and what does it mean? So you have never heard of this term before, so it's going to be brand new for you. Basically, we're going to try to find is narrow down where the mean or a statistic will be in a population based on the information we're given. So a confidence interval is a horizontal region under a normal density curve that we are confident the population mean will be within. So we're trying to find out, like based on the samples or based on the information we're given, how confident are we that the mean of the population will be there? So for example, like if we find the average height of people at Logan, and then maybe the average height of people at Logan Middle, and if we find more information like that, can we estimate the average height of all people in the entire world, which would be the entire population? So things like that. They are used for estimating the true value of the population parameter, and they are only accurate when done with a random sample or randomized experiment. Okay, so the formula for calculating the confidence interval for a population mean. So for a simple random sample of size n from a population having an unknown mean u and a known standard deviation sigma, a level C confidence interval for u is right here. C, which stands for how confident we are, is equal to x bar plus or minus z star. This is a new term for a z star is different than z. So z star, and then we have sigma, which is the standard deviation, divided by the square root of n. Okay, and I just want you to know that this will be given on your test, or you can use this note sheet for your test, so you don't have to memorize this equation. But x bar is the average of our sample. Z star is actually on this chart. So I'm gonna scroll down, way down here. So I go way to the bottom. On this chart on Canvas, there is Z star. So Z star has these percentages. This is what we're talking about when we say Z star. Okay, so those percentages are the confidence level C. It even says that right here, confidence level C. Okay, so we're gonna use that chart. So if you don't have that, if you have the chart on Canvas, open it up. If you have the chart, the hard copy, the paper, take that out because you'll need that. So there's the equation for confidence interval. And Z star is the upper critical value for the standard normal distribution found on the bottom of your Z-scores table. So that's what we just showed you. So properties of confidence intervals. The user chooses the confidence interval and the margin of error follows from this choice. We want a high confidence. Okay, so the higher the confidence, the better. And we want a low margin of error. So high confidence says that our method almost always gives correct answers, and a low margin of error shows that we have pinned down the population parameter. So it's low margin of error and a very high confidence. So margin of error is equal to Z star times sigma over square root of n. Okay, and that is this part right here. So that is the margin of error. And the margin of error gets smaller as Z star gets smaller. So a smaller Z star means a smaller confidence interval because it brings the critical values back in towards the mean. The higher the confidence level, the wider the confidence interval. Okay, so let me draw a picture. What this means is in your normal curve, here is the mean. So the smaller the z-score, the closer it is to the mean. The wider the z-score, or the higher the confidence level, the farther it is from the mean. So if we have a really skinny region from the mean, like the top one, we're going to be less confident than if we have a really wide margin of error. So that's kind of one example. The higher confidence level means a wider confidence interval. The smaller confidence level means that it's a smaller region. It's closer to the mean. It's kind of like saying, like, if we're talking about heights, I'm just going to throw a few numbers out there. If the average height is 65 inches, okay, if we picked a random person, the chances of them, let's say, being 60 to 70 inches is less likely than them being like 50 to 80 inches tall. So the bigger that region, the more confident you are. That's kind of what that's showing. So the wider the region, the more confident. The smaller that region, the closer it is to the mean, the less confident. Number 2, it says, as the standard deviation, or as sigma gets smaller, if the variation of the population decreases, the variation in the samples will decrease, allowing us to narrow down the location of our mean. So the less spread out, the smaller the standard deviation, the better we can narrow down our mean. If it's really, really spread out, it's harder to find the mean. But if the data is less spread out, means a smaller standard deviation, the easier it is to narrow down and figure out where the mean will be. And then lastly, the margin of error gets smaller as n gets larger. So if you increase the sample size, it reduces the margin of error for any fixed confidence interval. Okay, so the examples hopefully will make this a little more clear for you. So it says, here's a random sample of points scored by the boys basketball team over the past 20 years. Find a 95% confidence interval for the average points scored by the team. So what we have is, think about the last 20 years. There were a lot of basketball games played in the last 20 years. And right here is just a random number of scores. So what we have is there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 scores. So n equals 10. Because that's from 10 games. So we're saying if we take these 10 games, can we figure out where the average number of points is for the last 20 years? Now, just so you know, this would be really, really hard to do because if you're looking at 10 games, the last 20 years, there might have been 500 games played in the last 20 years. So if you're only taking 10 games to try to find out what the average points scored by the team was, it's going to be pretty hard, which is why there's a confidence interval. We want to be 95% confident that the mean is going to be within these two numbers. So we're going to kind of narrow it down to say, well, the mean is probably going to be between here and here, because it's impossible to actually find it out unless you know all of the games. So we know n is 10. Okay, to find the average of our sample, you would add them all up. So just so you know, when you add these all up, 68 plus 62 plus 75 plus 54, add them up, you would get 602. So 602 divided by 10 is 60.2. So the average of the 10 games we picked was 60.2. Okay, and we know there's 10 games, so n is 10. The standard deviation is 4.4. Okay, and then z star. This is the first time we're going to look up z star. Z star we want to find for 95% confident. So we're going to go to our table and find 95%. So I scroll way down to the z star, the confidence intervals. Way down here. 95% is right there. The confidence level of 95% would be 1.960. That would be our z star. 1.960. So z star is 1.96. So let me scroll up here. 1.96. All right, so we have everything we need over here. The n, the x bar, the standard deviation, and then z star. So remember the equation from above? C equals, and I'm talking this equation right here, x bar plus or minus z star, and then standard deviation divided by square root of n. So x bar plus or minus z star times sigma divided by square root of n. So that's the equation we're going to follow. So that means that C equals 60.2 plus or minus 1.96 times 4.4 divided by the square root of 10. Okay, so if we use our calculator, that would be 60.2 plus or minus 2.73. Okay, so if we take 60.2 minus 2.73, that would be 57.47. And if we take 60.2 plus 2.73, you would get 62.93. So our confidence interval will be 57.47 to 62.93. And what this means is that we are 95% confident that the true mean lies between 57.47 and 62.93. So again, if we only take 10 games, right, 10 scores from the games, and we found the average, we cannot find the exact average of the last 20 years. But we can use confidence intervals to find out that we are 95% sure or 95% confident that the average of the games from the last 20 years would be between 57.47 and 62.93. So that means we're pretty sure the average of the last 20 years is between these two numbers. So we can narrow it down to that range right there by doing a confidence interval. And that's what we're trying to do, because it's nearly impossible to find the average of the last 20 years, but we can kind of narrow it down to what the true average or the true mean is. Okay, and then in number 2, it says, a manufacturer of video terminals must control the tension of the mesh of the fine wires that lies between the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. So tension is measured be an electrical device in millivolts. Careful study has shown that the standard deviation of tension measurements is 43 millivolts. So we have our standard deviation. Right, here are the tension readings from a simple random sample of 20 screens for a single day's production. Construct a 90% confidence interval for the mean tension of all screens produced. So what we know is standard deviation is 43. We know that n equals 20 because it says 20 screens. Okay. X bar is going to be equal to what you get when you add all these up. So if you add all these numbers up, 269.5 plus 280.4 plus 264.7 plus 342.6. If you add them all up, you will get 6,126.4. To find X bar, you will divide that by 20. 6,126.4 divided by 20 is 306.32. And then Z star is what we get when we have 90% confidence interval. So we have to go to our chart, 90% confidence interval. So go way down here. 90% is right here. So 90% confidence interval is 1.645. 1.645. So scroll up. 1.645. So we gotta do our equation, the C equation. So C equals X bar, which is 306.32, plus or minus Z star, which is 1.645, times the standard deviation, which is 43, divided by the square root of n, and this time n is 20. So the confidence interval is 306.32 plus or minus, now let's type in our calculator, 1.645 times 43 divided by square root of 20. We will get 15.82. So the confidence interval is what you get when you subtract 15.82 from 306.32, or when you add 15.82 plus 306.32. So we will get 290.5 when you subtract 15.82, and you will get 322.14 when you add it. So the confidence interval goes from 290.5 up to 322.14. So we are 90% confident that the true mean lies between 290.5 and 322.14. Okay, because we cannot find the exact true mean, but we can find out that we're 90% sure it's between these two numbers. So we kind of narrowed it down to those numbers. Okay, and if you notice in this group of 20, some numbers are bigger than 322, some are less than 290, but we know that if we did all of these screens, if you took every single screen ever made, if you could possibly do it, you would find out that the mean is between 290.5 and 322.14 millivolts. We're 90% confident of that. We're not positive, but we're 90% sure. All right, and that's the two examples we got on confidence intervals. We're gonna practice more of these in class when I see you next.